Hello everyone, this is Safo and welcome back. In the previous video, we learned how to analyze a control system in the frequency domain using the Buddha plot. Another important tool for frequency domain analysis is the Nyquist plot. The Nyquist plot provides valuable information about system stability and is widely used in classical control system design. In this video, we learn how to generate and interpret a Nyquist plot using MATLAB. So let's get started. Okay, first, we clear the MATLAB environment. The CLC command clears the command window. The clear command removes all previously stored variables, and the close all close any open figure windows. This ensures that we begin with a clean workspace. Okay, next. We define the transfer function of our system. The numerator is equal to 100. The denominator represents the polynomial s squared plus 10s plus 100. Now we create the transfer function model. The tf command creates the transfer function and stores it in the variable g. And next here, we display the transfer function in the command window. This allows us to verify the mathematical model before performing any analysis. Okay, and now let's here plot the step response. First, we create a new figure window. Then the step command here generates the step response of the system. The grade command improves readability. Finally, here we add a title and access labels. Although today's focus is the Nyquist plot, reviewing the step response helps us relate frequency domain analysis to the system time domain behavior. And here now we generate the Nyquist plot. Again, we create a new figure window. The Nyquist command computes and plots the frequency response of the system on the complex plan. The horizontal axis represents the real part of the frequency response. The vertical axis represents the imaginary part. Finally, we enable the grade and add a title here. And next, okay, here let's display the pole zero map of the system. The PZ map command displays the location of the poles and zeros on the complex plan. This plot helps us understand how the pole location influences the system dynamic behavior and stability. At this point, our code is complete. Let's run the script and examine the result. Okay, run. Okay, first here we can see MATLAB display the transfer function in the command window. We can see here. we can see that the transfer function is 100 divided by s squared plus 10s plus 100. This confirms that we are analyzing a second order system. Okay, here. Now let's examine the first figure. This is the step response of the system. The output rises quickly. You can see, exhibits a small overshoot, and finally settles at its steady state value. This indicates that the system is stable. Now let's look at the Nyquist plot, figure 2. The curve begins near the point 1 plus 0j, corresponding to the low frequency response. As the frequency increases, the curve moves through the complex plane and it gradually approaches to origins. Notice that the curve does not encircle the critical point negative 1 plus 0j. For this system that indicates stable behavior, the Nyquist plot is one of the most powerful tools for evaluating closed loop stability. Okay, and here, figure 3. Finally, let's examine the pole zero map. In this figure, MATLAB displays the poles of the system. Our transfer function has two complex conjugate poles. Since the numerator is a constant, the system has no finite zeros. The pole location helps explain the behavior observed in both the step response and the Nyquist plot. In this video, we learned how to generate and interpret a Nyquist plot in MATLAB. We also reviewed the system step response and examined its pole location to better understand its frequency domain behavior. In the next video, we will use both the Bode plot and Nyquist plot to calculate gain margin and phase margin, two important measures of system stability. Thank you for watching.